Hi, welcome back to Math 533, Topics in Euclidean Geometry. In this video, we're going to take a look at our two similarity theorems from last week. The first one of these is the angle similarity theorem for triangles, which says that two triangles are similar if and only if their corresponding angles are congruent to each other. Many of you learned this in high school as the definition of similar triangles. And then the second property we're going to look at is a theorem that you proved half of on last week's homework, and the second half of it you're going to flesh out on this week's homework. But this is the side-side-side similarity theorem, which tells you that two triangles are similar if and only if their sides have a common ratio from the first triangle to the second triangle. Okay, let's go ahead and prove these theorems. Let's start with the statement of the angle similarity theorem. Triangle ABC is similar to triangle DEF if and only if the angle in A is congruent to the angle in D, the angle in B is congruent to the angle in E, and the angle in C is congruent to the angle in F. This is an if and only if statement, so we need to prove two directions. We have a forward implication, so we assume that the triangles are similar, and then we want to conclude that the angles are congruent. And then the other direction is we assume the angles are congruent, and then from that we want to conclude that the triangles are similar. And as we should recall, we say the triangles are similar if there exists a similarity transformation that maps one of them to the other one. Okay, so let's start with the forward direction of this proof. By hypothesis, there is a similarity transformation T with ratio C greater than 0, so that T of A is D, T of B is E, T of C is F. Okay, I already have the letter D as the name of a point in this problem, so I'm going to use H to indicate the dilation centered at A of ratio C. And I'm going to define B prime and C prime to be the images of B and C respectively. All right, so here's my point A here on the left, and I don't remember what ratio I used, but whatever it is, it's the same ratio C as the one for my similarity transformation T that is part of my hypothesis, right? So the equality, the fact that it's the same ratio in both cases, is an essential part of the argument. Okay, by the theorem of Thales, the basic proportionality theorem, this segment C prime B prime is parallel to the segment CB. And that's because the ratios AC prime over AC, that's that constant C, but AB prime over AB is also that same constant C. Now using, I guess technically the converse to the alternate interior angles theorem, this tells me that the angle in B prime is congruent to the angle in B, and the angle in C prime is congruent to the angle in C. And now we're going to use a piece of the homework that you would have done if you were taking the class for graduate credit, which is to say that if you take your favorite dilation and compose it with an isometry, you get any of the similarity transformations that you like. So given our similarity T and our dilation H, and they have that same constant C, then there's going to exist an isometry phi, so that we can say that T is the composition phi composed with H. And now just thinking about what composition means, that means, right, H sends ABC to A B prime C prime, but T takes ABC to DEF over here. So what that tells us is that the isometry phi sends the triangle A, B prime, C prime to the triangle DEF. And in particular then, A, B prime, C prime is congruent to DEF. And so my two little triangles in my picture are congruent to each other. But now using the angle identities that we have, well, so the angle in D is then forced to be congruent to the angle in A. The angle in E is congruent to the angle in B prime, but as we observed earlier, the angle in B prime is congruent to the angle in B. And finally, the angle in F is congruent to the angle in C prime, which is then again by this fact up here, congruent to the angle in C. So that completes our proof of the forward direction. Okay, we finished proving the forward implication of this result. Now it's time for us to do the backwards implication of our if and only if statement. So remember, we now assume that the triangles ABC and DEF have the property that the angle in A is congruent to the angle in D, the angle in B is congruent to the angle in E, and the angle in C is congruent to the angle in F. And now we're going to basically make the same construction just going backwards. So we construct B prime and C prime on the rays AB and AC so that the distances, the distance AB prime equals the distance DE, and I'm going to make the angle in B prime be the same as the angle in E. So now I can say by angle side angle that triangle A, B prime, C prime is congruent to So now I can say by angle side angle that triangle A, B prime, C prime is congruent to triangle DEF. And as we've seen before, if two triangles are congruent, then there exists an isometry. As a matter of fact, there exists a unique isometry that sends one of them to the other one. So in this case, sending A, B prime, C prime to DEF. Okay, leaving this aside for a second, right, we constructed the angle in B to be congruent to the angle in B prime. So by the alternate interior angles theorem, we have that B prime C prime is parallel to BC. So now by the theorem of Thales, we can say something about the ratios of those side lengths. That AB prime over AB equals AC prime over AC, calling that ratio C. And now I look at the dilation centered at A with ratio C, and that sends B to B prime, C to C prime. And now we compose our isometry phi with this dilation H, and that gives us the similarity transformation we want. And that finishes the proof of the backwards direction. So now let's talk about the side-side-side similar triangles theorem. So this one, the proof you're going to do, but let's remind us of the statement first. So triangle ABC is similar to triangle DEF if and only if there exists a constant that's positive so that DE is that constant times AB and DF is that constant times AC and EF is that constant times BC. So in other words, if and only if the ratios work out the way we want them to. Okay, on the week 11 homework, you proved the forward implication. So the only part that's missing is the backwards implication. So we can go ahead and assume we have triangles so that there exists a constant so that we have the sides come in the appropriate ratios. And then we want to construct a similarity transformation T that does the job. Now, there are many ways of doing this, right? We can directly construct the similarity transformation T, or actually we can go ahead and use the angle similarity theorem. It's up to you exactly how you work that out. But the key trick to do is to consider the dilation centered at A of ratio C, right? And that gives you points B prime, C prime. And really what you want to do at that point is to show that triangle A, B prime, C prime is congruent to triangle DEF. So take a look at that on the homework and see if you can figure out the details of that argument. Okay, that's it for this video. Thank you for watching. I hope you enjoyed it. And that wraps up our proofs of our basic, I'd say, structure theorems for similarity of triangles. In our next videos, we're going to take a look at consequences of similar triangles and how that influences properties of lines in those triangles. Thank you for watching. See you on the next one. Happy mathing.